today's lecture we are going to discuss about the reciprocal space and Wigner-Seitz cells relationship between energy and the wave vector. Where energy E and wave vector, which was E equal to h bar square k square upon 2m, at where wave was the wave vector k was 2 pi upon lambda, where lambda is the wavelength associated with the de Broglie wavelength. Like any electron or particle, if it is moving, there is a wavelength corresponding to it. And there we see if the electron are nearly free, then the relationship between the energy and k is a parabola. Like there was something like this, the curve was something like this. And for the bound electron, there is a discretization of this energy versus k was not continuous, but the energy exists for only for the specific value of k. We were like 2 for nearly free for bound electron, this was 2 pi upon k, and for nearly free electron, it was 2 pi upon L, where L was the length of sample. Now, this L being very big, of course, in relation to the atomic scale distance, it's very big. So, what is happened? The spacing between energy is very close. They are very close to each other. Uh, it is so close that it looks like a continuous. Like now, why we are specifically going for the reciprocal space? Because reciprocal space, what we do, we have an atom arranged in a real space. We can translate this into a reciprocal space, which will define as a more elegant way of describing certain phenomena such as diffraction, including X-ray diffraction, transmission electron diffraction, which we use to study the crystal structure and many other material properties. Since electrons are also behave as a wave, so they are also internally diffracted. Now, for in a real space, like there is an atom arrangement, and they are described with the vector a1, a2, and a3. These are three vectors. They are defined. Now we want to just translate a mathematical way of describing it into a reciprocal space. Where they are described as reciprocal lattice vector b1, b2, and b3. And there is a relationship between them, a1, a2, a3, and b1, b3, which is described as like b1 is a2 cross a3 divided by a1 dot product of a2 cross a3. This is how we describe the reciprocal lattice vector b1. Similarly, b2 is a3 cross a1 upon a2 dot product a3 cross a1. And b3 is a1 cross a2 upon a3 dot a1 cross a2. So this is how we describe all of them, b1, b2, b3. It is actually a relationship between real space and the reciprocal space. Now let's consider for the very simple case, which is cubic. Let's say in real space we have a structure which has a cubic uh, crystal structure or symmetry. In that case, it will be A1 will be A the which is distance, lattice constant A x, and A2 will be A y direction, of course. A3 will be A z. Now let's use these equations to see how it turn out to be. So first of all, A2 cross A3, and it will be A square and x y z. A2 cross 0 1 0 0 0 1. So it will be A square will be A square will be 1 minus 0 plus 5 cap minus 5 cap. It will be 0 minus 0 plus that cap. It will be again 0 minus 0. So basically A2 cross A3 is A square X cap. Now let's do the dot product. A1 dot A2 cross A3, and it will be A X square, and with the dot product A square. So it is basically A cube, because X cap dot product with the X cap will be A3. So overall B1, which we defined was A2 cross A3 upon A1 dot product A2 cross A3, it will be A square X cap upon A cube. Will be basically 1 upon A X cap. Similarly, if we do for other, U2 will also be 1 upon A, this will be Y cap, and B3 will be 1 upon A Z cap. So basically, in the real space, if the structure is cubic, in the reciprocal space, it will also be a cubic, just that it will be 1 upon A. It will be just distance 1 upon A, it will scale by 1 upon A. A cubic in a real space will also be a cubic in a reciprocal space. Now let's move forward. Let's see the case of FCC. Let's see the case of how the FCC lattice will behave. FC stands for phase center cubic. We have a cubic system. These are the axis, x-axis. These are the y-axis. This is the z-axis. And first, this is a cubic. So every corner will have one atom. And this is axis. So there will be one more atom on every face. For simplicity, I will be drawing only for these three phases. There will be one at the bottom, one at this face, and of course one at so A1, A2, and 3 is a real space vector. So if we define, it will be A1 will be A by 2. So basically half of distance in y direction and half of distance in z direction. So it will be y cap plus z cap. And similarly, A2 will be A by 2. In y direction, it will be A2 will be of course in half direction in x direction and half direction in, in the z direction. And similarly, A3 will be A by 2, half direction is y direction and half in z direction. So these are the real space lattice vector. Now for them also let's do B1, which we described B1, A2 cross A3 upon A1 dot A2 cross A3. Now for A2 cross A3 will be A square by 4 and Z. So it will be 1 0 1 and 1 1 0. Will come out to be A square by 4. X will be 0 minus 1 minus y. It will be 0 minus 1 so it will be 1 minus 0. So basically A2 cross A3 will be A square by 4 minus x cap plus y cap plus z. Now let's multiply it with the A1 dot product of A1 with A2. It will be A1 will be A by 2 y cap plus z dot product A square by 4 x square plus n it will be A cube by 8 and will be 1 plus 1. It will be A cube by 4. Why the dot product is 1? This is because when if there are two vectors A, let's say A and B, and if they are, and we know dot product is given as mode of A, mode of B, cos theta. And if theta is 90 degree, they are orthogonal. So cos 90 is 0. So this will be 0 dot product. So basically, x dot product with y will be 0. So only x dot x will be cos 0, which will be 1. So y dot y will be 1 and that dot z1 will be 1. Other thing will be 0. So this is what's the value of a cross 1 by 3. A dot a cross A2 cross A3 is now B1. So which we mentioned earlier is defined, which we defined as A1 dot A2 cross A3. So it turned out to be A square by 4 upon minus x square plus y plus b upon A cube by 4. So it turned out to be 1 upon A. 1 upon A square plus y square plus b upon A cube by 4. So it turned out to be 1 upon A. 1 upon A cube by 4. So it turned out to be 1 upon A minus SPF plus. So this is B1, and similarly, if we do, we will also get B2 to be 1 upon A minus SPF minus 5, and B3 will be 1 upon A SPF plus 5 minus. So basically, what is showing that again it will be 1 upon A, but at this time these are the coordinate of the body center cubic. So basically FCC in real space convert into BCC body center cubic in a reciprocal space. Let's move forward and go to the concept of Wigner-Seitz cell. To the lattice. Fine. So this is, let's consider this is a 2D lattice, and is the closest, and this is origin, and the closest to this is this neighbor, and this is also neighbor, closest neighbor. These four are its closest neighbor. And also this. So this area is the Wigner-Seitz cell. So this is the closest. So we have a center point origin, and the closest point, the closest lattice point was this. We draw a perpendicular to the distance for in every side, and the area that is enclosing is called Wigner circle. This is in real space, but in reciprocal space, this become Brillouin zone. So Wigner site in real space, when we do it for the reciprocal space, become Brillouin zone. And this line become bragg plane, we consider 2D case. And if whenever there is a wave vector touching the bragg plane, there is a diffraction that is happening. Right. So let's consider now. Let's consider for the this simply again this thing again, but for the reciprocal space. Let's say this now. This time it is in reciprocal space. So closest to this point, these are these all are first nearest neighbors. And these are the second nearest neighbors. After first, these are the second which are closer to the origin. And if we draw a line, and this, if we also attach this with the second neighbor, that's what I mean. Now for the first neighbor, let's do the perpendicular bisector. It will go like similarly for this. And similarly for this, it will go right. So this area This area is called first Brillouin zone. First Brillouin zone. Now, if you do the same for the second nearest neighbor, like this, and if you do like this from this origin to this, and do the perpendicular bisector, of course, we do perfectly. So, and so this is basically I am bisecting this line, second nearest neighbor. These, right? So the area that is this area, which are outside building 1 2, and there was this area. So this area, which is this triangle, it is actually second building zone. So first building zone is actually when we closest to the first nearest neighbor, and for the construction of second Brillouin zone, we take the second Brillouin zone. But for the condition for the second Brillouin zone is that it should cross the first Brillouin zone or first black plane only once. So these are actually planes, the black plane. So this should close only once. So that's why if we go from this side to this side, and it cross only this point, and now it is ready. So this area is correspond to the second Brillouin zone. And if we add this triangle, this four triangle, this actually again is the same area as of this rectangle. So every Brillouin zone has actually the same area. Now let's move forward. On that in reciprocal space is actually do the scaling is 1 upon a in the reciprocal. The real space it is a, so then in reciprocal space it equals 1 upon a. And we know also the wave vector k and is actually 2 pi by lambda. Is also the is, is similar to the reciprocal space k space. It's just that it is multiplied with a factor of 2 pi, scaling of 2 pi. It doesn't change any symmetry of or anything. It's just that it is scaling. It's multiplying with 2 times. It is just expanding. Otherwise, it remains the same. So in the k space, in a real k space in the reciprocal space, it is also 2 pi by a. Now let's draw this reciprocal space, the EK energy diagram. So let's say E, and this time let's say I taking it little forward 2 pi by A, and again this will be 2 pi by A on this time will be, right? And we say the let's do the black plane or half. Let's say this is the closest point, and so half of this somewhere here. If we so, so this is the black plane. So these are all are black plane, and we know the energy versus K. Uh, it was parabola. Something like that, right? And so this is E versus K. But as you know, when a K vector is interacting with the fragment, there is a diffraction happen. Diffraction is happening. This will modify this EK. That's why I'm erasing it. So I will show it again. And then what is happening is when it interacts with the source of side, and this will also at downside. And similarly for this one, it will go down, go up, down, it will go up, go down. So, so the, at the fragment, the diffraction happening is changing. It. So what will happen to this curve? If we see, so there is a gap between energy. So we plot, right? So, so this is one energy, and width of this is again an energy band. Go forward in this direction. Again, another energy band where electron can exist. This energy there is no energy, so forbidden energy gap. So electron will not exist. Picture is called extended. This kind of diagram is called extended Brillouin zone. Now this we made all this by assuming that this midpoint is actually origin, but it's symmetrical all over. There is no need that origin will be origin can be here, origin can be here, or origin can be here, can be in multiple things. So suppose if the origin is here, then how it will look like? It will look like this. This will also become like this. Similarly, it will be like this. Similarly, like this. And similarly like this. This kind of representation is called repeated Brillouin. So this is sometimes that's why when you see a diagram, this is how. That's why when you see this is called repeated Brillouin zone. That's why when you time multiple time when you draw a diagram, UJ diagram, this is how it is shown. But still it is symmetrical all over. So and we know that this single zone, if we plot only this, the first building zone, it is identical because it is repeating. So all the information that are there, it is also available in the first building zone itself. So this in that picture is called reduced building zone. Uh, this is how the energy EK K versus energy diagram comes. So what we see overall, if we see, okay, electron is moving inside the solid, there will be a bound electron which can lead the discretization of energy. Like energy is not continuous, uh, but only at specific value of k. Then there is a free electron, then there is a nearly free and bound electron. For nearly free electron, the energy is the k value is 2 pi upon L, L being very large, so they are very closely spaced. And we say that we can represent mathematically crystal structure in a reciprocal space, which is usually 1 upon A. Depending upon its geometric or spectry, it can, like for example, FCC was in BCC. We saw this, then we saw if we try to plot this, we introduce the concept of the Brillouin zone with the nearest neighbor, and we cut it with a bragg plane. And when the k vector is interacting with the bragg plane, then there is a diffraction happening, which lead to the change in the band gap energy, the opening energy is not continuous. When we plot this for 1D curve, uh, then we see it was a continuous curve. When because of the bragg plane, it which there was a gap between them, like this gap. So it changed the curve, but we can take the origin anywhere or anything because it's symmetrical all over. So this kind of a curve where it's like maybe this structure is called repeated building zone. But overall this information is symmetry, so we can also reduce it. We say the whatever information that can we get from the complete structure, we can also get it for the single building zone. This concept is called reduced building zone.